Okay. So thank you. So first, I would like to thank you, Marta and Renato, for the invitation. And so these 3 to 1 foliations I talk about are kind of transverse foliation. So first, I will explain what are these objects. And then I will recall some previous results on the existence of transverse foliations for red flows on the tree sphere. Then I will explain some new results about the existence of these 3 to 1 foliations and give an example of Hamiltonian admitting these foliations. So in general, transverse foliation for any flow in a tree manifold, not necessarily just a tree, is actually a singular foliation. We have a singular set formed by a finite set of periodic orbits that we call binding orbits. And in the complement of this set of orbits, we have foliation, an actual foliation, where each leaf is transverse to the flow, and each leaf has boundary in a subset of the set of binding orbits. So one particular case of these transverse foliations would be is a open book adapted to the flow. In the case of an open book, we have just one family of leaves. All of them are diffeomorphic, and all of them have a boundary in the same length. So, like in this picture here, you can think of this as a transverse section of your manifold. So, these dots here represent an orbit, like entering the screen and exiting the screen here. And these are disks transverse to the flow. So in this case, this is the simplest case of a transverse foliation, where you have just one family. But in general, you can have several different families. You can either have like rigid leaves that are not part of a family, or you can have families parameterized by intervals. And yeah, basically that is, you can have different kinds of families with boundary in different subsets of the binding orbits. And the idea of transverse foliation is that you can somehow organize the flow. Like, for instance, in this picture, you have a finite set of leaves so that all of the orbits of the flow intersect at some of these leaves. So it's not as good as global surface of section, but you can extract some information. Sometimes you can prove the existence of periodic orbits or homoclinics and positive entropy and these kind of things. So I will talk about transverse foliations can work for can be defined for any flow, but I just talk about red flows on the tree sphere. So let me just recall some definitions. A contact form on S tree is just one form that is such that lambda wedge the lambda is nowhere zero, is a volume form. And associated to a contact form, we have the contact structure defined as its kernel. And we have the red vector field that can be defined by these equations. It's by defining that it's in the kernel of the lambda that is one-dimensional, and it's normalized by 1. And we call the red flow is just the flow of red vector field. And we will consider the tight contact structure on S3. It's just defined by the kernel of this canonical Liouville form, lambda 0. And in general, if you have any Hamiltonian flow on R4 with its canonical symplectic form, and you have an energy level that is regular and star-shaped, like in this picture here. And so if you restricted your Hamiltonian flow to this star-shaped energy level, this Hamiltonian flow is equivalent to a Reeb flow associated to contact form that is a multiple of lambda 0 that we call a tight contact form. So basically, every time I say something about Reeb flow associated to a tight contact form, you can think about Hamiltonian flow restricted to star-shaped regular energy level. Okay. So let me recall some previous results on the existence of transverse foliation. I think the first result on the existence of these objects for Reeb flows on S3 was a theorem of Hoffer, Vysotsky, and Zender. They proved that any tight contact form on S3 admits transverse foliation if lambda is non-degenerate, right? So, and they to prove it, they introduced the notion of finite energy foliation. They used the theory of pseudo-holomorphic curves in symplectization. So they defined what is a finite energy foliation. That's essentially foliation in the symplectization by finite energy pseudo-holomorphic curves. And when you project this foliation to S3, you have a transverse foliation, and you have some possibilities for the binding orbits and the leaves. So all binding orbits have Conley-Zender index 1, 2, and 3. The leaves have GNO 0, are punctured spheres. But in general, a question that we still have is which Reeb flows have which kind of transverse foliation. So for the dynamically convex case, in particular for strictly convex energy levels, we know that we always have a disk-like global surface of section. Actually, a one-parameter family of these global surfaces of section forming an open book. And for general tight Reeb flows, but non-degenerate, we also have a characterization of the orbits that bounds this like global surface of sections, or that are bindings of the open books that determined by these global surfaces of section. But for more general transverse foliations, we don't know. We don't have any characterization. We don't know which Reeb flows admit which kind of transverse foliation. So, and the first result about the existence of a transverse foliation that is not an open book, that is not the simplest possible, was a theorem by Nayara de Paulo and Pedro Salomão, and they proved the existence of a foliation that's called 3-2-3 foliation. Its name is because of the Conley-Zender indices of the binding orbits, and they gave examples of concrete Hamiltonians admitting these foliations. And of course, these Reeb flows are not non-degenerate, as in the case of this theorem. This makes things harder, of course. But these foliation is one of the possibilities obtained by Hoffer, Vysotsky, and Zender anyway. So the foliations I will talk about are called 3-to-1 foliations, also because of the Conley-Zender indices of the binding orbits. And basically, they are defined like this. We have 3 binding orbits with Conley-Zender index 1, 2, and 3. Like this one is the index 2, that is hyperbolic. We can see the projection of the stable and unstable manifolds here. This one is index 1, and this one is index 3. Again, you should see this picture as a transverse section of S3, and you can see this as a decomposition, as that the composition of S3 into two solid tori. So here we have torus formed by two cylinders, here and here. And it divides S3 into two solid tori, like this one is a solid torus foliated by disks. And this side here is a solid torus, but foliated by cylinders here between this orbit with index 3 and this orbit with index 1. So yeah, basically that's it. Okay. Yeah. So I will present some results about giving some conditions for the existence of these 3-to-1 foliations. And so let me explain the hypothesis we'll consider. So we'll fix an tight contact form in S3, and we will assume that we have three periodic orbits, like we call P1, P2, and P3. The name is because of their Collision index, so index 1, 2, and 3. So we assume they are trivial knots, and they are not linked to each other. And we have this hypothesis that this index 2 orbit does not admit a sphere like this, like where it's not the equator of an sphere transverse to the pole. So, and actually, this hypothesis actually hypothesis. Sorry, I forgot to mention that. Actually, I'm asking for for the non-existence of a strong transverse section, but it is stronger than being transverse. But I don't have time to explain exactly. But you can think of it as being just transverse, okay? Because this hypothesis is weaker than asking for the non-existence of transverse sphere. And this is quite maybe a strange hypothesis to check, but actually all these hypotheses are necessary to the existence of transverse foliation. We can prove that if you have 3-to-1 foliation, then you cannot have a sphere like this. Okay, so you'll consider this hypothesis from now on. And the first result about the existence of 3-to-1 foliation will be like this. I forgot to mention this was basically proved in my PhD thesis from last year. I haven't written here. So if you assume that all the orbits with small period are non-degenerate, and that this orbit P2 is the only one that has small period, condensing index 2, and is not linked to P3, and that P1 is the only orbit with small period that has condensing index 1 and is not linked to P2. Then if we have one of these leaves here, one of these disks asymptotic to the orbit with index 3, and if these disks come from a pseudo-holomorphic curve, if it's a projection of a finite energy pseudo-holomorphic curve, then you can use several different techniques from the theory of finite energy curves, like Fredholm theory, compactness, and intersection, and gluing theorem, all of these. And in the end, we can show that we will have all the foliation, all of the 3-to-1 foliation. And so another result that is with a different set of hypotheses, but that is more suitable for applications, because we don't ask for non-degeneracy. We don't have any hypothesis of non-degeneracy, but we need some more stronger hypothesis. Is that if your orbits have if your candidates to binding orbits have periods that are close in this sense, and if these orbits P1 and P2 are the only orbits that have small period and are not linked to P3. So all other orbits either have have large period or are linked to P3. And now you have to assume more things. Like you have to assume that you have one of these disks and one of these cylinders coming from pseudo-holomorphic curves. Then again, using a lot of techniques from the theory of pseudo-holomorphic curves in simplicizations, we can show that we have the complete foliation after this. So the idea now, I will not explain, instead of explaining the proof of this, I will show how I can check this hypothesis in a real example, in a real Hebb flow. So you consider this Hamiltonian. This is a somewhat simple Hamiltonian because it's separable. It's the sum of two Hamiltonians. So the first one is defined like this. The energy levels are just circles. And the second one is defined like this. It depends on 5 parameters, on epsilon that it can be considered very small, and A, B, C, and D. So if we choose appropriate parameters, this function will look like this. We will have exactly 3 critical points. And here is a saddle point. Here we have maximum, local maximum, and a minimum here. And we can choose A, B, C, and D so that all of them are non-degenerate. So this will be this will define our Reeb flow. So, and we can check that for if you take epsilon small enough, the energy level 1/2 is a star-shaped hypersurface. It's a regular energy level and it's a star-shaped hypersurface. So, as I said in the beginning of the talk, this Hamiltonian flow restricted to this energy level will be equivalent to a tight Reeb flow on S3. So we can apply our results to this. So our candidates to binding orbits will be these 3 orbits defined like this. This will be the only orbits that when you project to the X2, Y2 plane, they will project exactly in these critical points. So when you look in the X1, Y1 plane, they will look like this. So their period will be given by pi r square, where r is the radius of these orbits. So because of this definition for the orbits, we can check that their periods are very close if you take epsilon small. Actually, for epsilon, these pictures are for epsilon equal to 1. But if you shrink epsilon, this orbit will be very close. Like these 2 are very close also already, but this blue one will be very close too. And of course, it's easy to see that it's a trivial link. And we can consider a suitable trivialization. Actually, it's a trivialization, the well-known trivialization that on R4 along the energy level that is given by a set group of matrices that are matrices that are isomorphic to the quaternions. So we can consider this well-known trivialization to compute their collision index, and it will be 1, 2, and 3, but they will be non-degenerate if epsilon is small enough. So the hypotheses on the orbits are checked. And actually, you can check all the other hypotheses. So that hypothesis about the non-existence of a sphere with a weight of P2 can be checked in this case because here, since it's a separable Hamiltonian, it's easy to see that the stable and unstable manifold will project exactly to this green curve here. So the idea is that if we do have a sphere with equator P2 that is projected to this critical point here, necessarily it will be something like this on segment here and some place here, and some part of the sphere will necessarily enter this region. And we can show that it necessarily will intersect the stable and unstable manifold. So we can use the fact that the lambda area in these manifolds are 0, and the lambda area in the transverse sphere is always positive, and we can get a contradiction by this intersection. So in this case, we can easily prove that there is no sphere like this. So the second hypothesis is that in this case, we can really check that we have one pseudo-holomorphic plane and one pseudo-holomorphic cylinder that asymptotic to the orbit with index 3, and the cylinder asymptotic to the orbit with index 3 and the orbit with index 1. Actually, we can use an idea that I learned from that paper by Nayara de Paulo and Pedro Salomon on 3 foliations. The idea is that you can use the symmetry of this Hamiltonian. In this case, we have symmetry in relation to the y coordinate, so that we can use this symmetry to transform the problem of solving Cauchy-Riemann equation, that is a PDE, into the problem of solving an ODE, that first order differential equation, because we can assume a priori that our plane is like this. It's exactly in the x-axis, and it has this form. And so when you put it into the Cauchy-Riemann equation, we will end up with an ODE in f of s and g. So we can actually solve this ODE, and in the end, we can show that there really exists these pseudo-homomorphic curves. So this hypothesis is checked. And the last one is that P1 and P2 are the unique periodic orbits that have small periods and are not linked to P3. So to check this hypothesis, we can show that in this region here for small epsilon, in this region here, the Hessian of the Hamiltonian is very small. And using this, you can prove that all the periods of the orbits in this region are bounded by this stable manifold, stable and unstable manifold. The periods are very large here in this region. And if you have an orbit outside this region, it will necessarily intersect positively a plane to P3, and you can think of this plane, for instance. So our orbits here outside this region will intersect positively, plane to P3, so they will be linked to P3. So we can check the last hypothesis too. So all the hypotheses of that theorem I talked about, I checked. So this Hamiltonian really admits 3-to-1 foliation. And the 3-to-1 foliation will look like this the projection of this 3-to-1 foliation will look exactly like this. So we have constructed the holomorphic plane, and it will be a part of this one parameter family of planes here. And we already had this cylinder between the index 3 orbit and the index 1 orbit, and it will be part of a one parameter family of cylinders too, and they will break in this rigid surface that is a cylinder here, another cylinder here, and a cylinder here also, and this rigid plane to P2. So this is the complete foliation. So yeah, that's it. I will stop here. Thank you.